Good morning. This is the second lecture on axial flow compressor. The contents of the lecture are the overall efficiency versus isentropic efficiency of the compressors and turbine. Then I'll discuss on polytropic efficiency, what is preheat and reheat. Then I'll derive the expression for overall pressure ratio of a multi-stage compressor. I'll initiate the discussion with overall efficiency versus isentropic state efficiency of compressor and turbine. Look here, the TS diagram represents the compression process of a compressor where P01 is the total pressure at inlet and P02 is the total pressure at the exit of compressor. And this compression occurs through number of stages. Thus, 1, 2s represents the isentropic compression and 1, 2 represents the actual compression, where del T0 indicates the temperature rise in a stage and the corresponding isentropic temperature rise is represented by del T0s. Similarly, for the turbine, the pressure drop has been indicated in the TS diagram, where N2 represents the actual process, where P01 is the inlet pressure and P02 is the exit from the turbine, exit pressure from the turbine, and 1, 2s indicates the isentropic process. Thus, with this discussion, I can now define the overall efficiency of a compressor as the ratio of ideal to actual work transfer. Thus, the efficiency of the compressor, eta C, can be defined as isentropic work transfer divided by actual work. Thus, eta C can be stated as H02s minus H01, that is isentropic enthalpy rise. This is the overall enthalpy rise divided by actual enthalpy rise, that is H02 minus H01. If we consider Cp with this temperature range stands constant, then I can write eta C as T02s minus T01 divided by T02 minus T01, that is isentropic temperature rise divided by actual temperature rise. Similarly, the eta T can be expressed as actual work divided by isentropic work. So, as a ratio of actual enthalpy drop to the isentropic enthalpy drop, and that can be also expressed in terms of temperature ratio. Thus, eta T is equal to T01 minus T02 divided by T01 minus T02s. Here, isentropic temperature drop for a turbine will be higher than the actual temperature drop. Thus, I have defined the overall efficiency of a compressor, that multi-stage compressors, and overall efficiency of a multi-stage turbine. Furthermore, please note that eta T tends to increase and eta C tends to decrease with increase of pressure ratio, for which the compressor or turbine are designed. Let us now consider an axial flow compressor consisting of number of stages. And this compression process through different number of stages has been indicated in TS diagram, where P01 indicates the inlet total pressure to the compressor and P02 exit total pressure. I have indicated also the different pressure line that occur through successive stages. Thus here, isentropic overall temperature rise is represented by 2S and 1, whether the actual temperature rise is indicated by 1 and 2. And for any stage, the actual temperature rise is indicated by delta 0, whereas the corresponding isentropic temperature rise for that stage is indicated by delta 0S. Now after this, if the blade design is similar in successive stages, it is reasonable to assume that isentropic stage efficiency eta S remains the same throughout the compressor. Thus, I can now define the stage isentropic efficiency eta S as the ratio of del T0S by del T0, where del T0 is equal to del T0S by eta S, del T0 being the actual temperature rise of a stage, where del T0S is the corresponding isentropic temperature rise, and eta S be the stage efficiency. Thus, I can write the overall temperature rise, that is equal to T02 minus T01 is equal to sigma del T0, that is summation of all temperature rise that occur through different stages, that would be equal to sigma del T0S by eta S. Now eta S being constant, so I can take out of the sigma sign, thus 1 by eta S into sigma del T0S, which is the equation number 10. Thus what the equation number 10 says, that overall temperature rise T02 minus T01 of the compressor is equal to 1 by eta S plus sum of all isentropic temperature rise through different stages. Now we can define again T02 minus T01 is equal to T02S minus T01 by eta C, considering the overall compressor. Look here, I can write actual temperature rise in terms of isentropic temperature rise and eta C, which is the equation number 11. Now, if we equate equation number 10 and 11, I can write eta S by eta C is equal to sigma del T0S divided by T0S minus T01. Now look, the constant pressure line in TS diagram are diverging. Thus, I can definitely say sigma del T0S, that is sum of all isentropic temperature rise through this stage, must be greater than T02S minus T01 for the compressor, and hence eta C is less than eta S for the compressor. Thus, I have concluded that for compressor eta C, that overall compression efficiency should be less than isentropic stage efficiency. Further, I like to say that the difference between eta S and eta C will increase with number of stages, that is, with the increase in pressure ratio for compressors. The physical explanation can be given as the increase in temperature due to friction in one stage results in more work required for the next stage, and it might be termed as preheating effect. That is, in case of compression, the frictional effect is considered as loss. A similar argument can be given for a turbine where eta T is greater than eta S, and this difference, that is difference between eta T and eta S, increases with the pressure ratio. Thus, in this case, the frictional reheating in one stage is partially recovered as work in the next stage. Thus, the frictional loss here is partially benefiting. So, what I like to tell that the total frictional loss is not wasted. The part of that can be recovered in the next stage as useful work. Furthermore, I have defined polytropic efficiency. The above consideration, as I have discussed before, has led to the concept of polytropic efficiency, or the small stage efficiency denoted by eta P, which is defined as the isentropic efficiency of the elemental stage in the process such that it remains constant throughout the whole process of compression and expansion. Thus, I like to say further, I'm considering the compression or expansion occurring through a large number of stages where the isentropic efficiency of this elemental stage is assumed at constant, and that is denoted by eta P. Thus, I can say for a compressor, eta PC is constant throughout the process 1-2, and it can be described as PV to the power n is equal to constant, where n is called the polytropic index. Further, if I consider the gas as ideal, I can write PV is equal to RT, thus V is equal to RT by P. Now substituting V from ideal gas relation to the polytropic process PV to the power n, I'll get P R to the power n T to the power n divided by P to the power n is equal to constant, which can be put in the form P to the power 1 minus n into T to the power n is equal to constant. Now, if you differentiate, it will yield n into dt by T plus within the bracket 1 minus n into dP by P. This can be reduced to dt is equal to n minus 1 divided by n dP by P into T, equation number 13. Now, I have indicated here the elemental stage in T and the compressor in the TS diagram, where dT0 is the actual temperature rise through this elemental stage, and dT T0s is the corresponding isentropic temperature rise. Thus, from equation 30, I can write for total temperature dT0 is equal to N minus 1 divided by N into dP0 by P0 into T0. Similarly, for the isentropic temperature rise for an elemental stage, dT0s is equal to gamma minus 1 by gamma into dP0 by P0 into T0. Please realize that when N is replaced by gamma, you land to the isentropic process. Thus, eta PC, which is the polytropic efficiency for the compressor, that is the elemental isentropic efficiency. So dPc can be written as dT0s by dT0, that is equal to gamma minus 1 by gamma divided by N minus 1 by N. Thus, for a compressor, I can write N minus 1 by N is equal to gamma minus 1 by gamma into eta Pc, where eta Pc be the polytropic efficiency of the compressor and N is the polytropic index. Similarly, for a turbine, I can derive the similar expression, which would be N minus 1 by N equal to eta Pt into gamma minus 1 by gamma, where eta Pt is the polytropic efficiency for the turbine. With reference to the TS diagram, where the compressor is consisting of large number of elemental stage and 1, 2 is the actual overall temperature rise, where 1, 2s is the isentropic temperature rise. Furthermore, dT0 is the actual temperature rise of an elemental stage, and the corresponding isentropic temperature rise is denoted by dT0s. After this discussion, I can relate between eta Pc, that is polytropic efficiency, and eta C, that is overall efficiency of the compressor. And thus, how this can be related, let me continue. I can write now eta C as T02s minus T01 divided by T02 minus T01, that the ratio of isentropic temperature rise to actual temperature rise, that can be written as T02s by T01 minus 1 divided by T02 by T01 minus 1. This is isentropic temperature ratio, and this is actual temperature ratio. So now this can be related with the pressure ratio as, so eta C I can now write P02 by P01 to the power gamma minus 1 by gamma minus 1 divided by P02 by P01 to the power n minus 1 by n minus 1, when n is the polytropic index. Now I have already correlated in eta Pc and gamma. Thus I can write eta C is equal to P02 by P01 to the power gamma minus 1 by gamma minus 1 divided by P02 by P01 to the power gamma minus 1 divided by gamma into eta Pc minus 1, where Eta PC is the polytropic efficiency of the compressor, and eta C is the isentropic efficiency for the compressor. This is overall efficiency for the compressor. Thus, 17 is an important relation which gives overall efficiency of a compressor in terms of pressure ratio and eta PC. Similarly, for a turbine, the overall efficiency eta T can be related with respect to pressure ratio and the polytropic efficiency eta PT. Thus, I can write here eta T is equal to 1 minus P02 by P01 to the power eta PT into gamma minus 1 by gamma divided by 1 minus P02 by P01 to the power gamma minus 1 by gamma, where eta T indicates the isentropic efficiency of a turbine, while eta PT is the polytropic efficiency. The figure here indicates the variation of isentropic efficiency of turbine and compressor, that is eta C and eta T, with pressure ratio for a polytropic efficiency eta P of 85%. What has been illustrated here, that eta C decreases with pressure ratio where eta T increases with the pressure ratio. Now the question is that for a given pressure ratio and the temperature ratio of a compressor or turbine, can I project the value of polytropic efficiency? The answer is yes. How would we do that? I have indicated here. From equation 15 that I have derived earlier, for a compressor I can write eta PC is equal to dT0s by dT0, that is isentropic temperature rise for the elemental stage divided by actual temperature rise, that can be projected as gamma minus 1 divided by gamma into dP0 by P0 into T0 by dT0. Or it can be written as dPc into dT0 by T0 equal to gamma minus 1 by gamma into dP0 by P0. Thus, integrate between the process 1 and 2, which is the compression process, considering eta P remains constant by definition. Thus, we can write eta PC is equal to ln P02 by P01 to the power gamma minus 1 by gamma divided by ln into T02 by T01. Thus, for a measured pressure ratio or temperature ratio, I can evaluate the value of polytropic efficiency eta PC. After a discussion on polytropic efficiency, let me discuss now on overall pressure ratio of a multi-stage compressor. And here, as indicated in TS diagram, the increase in pressure occurs through number of stages. I have already derived the expression for stage pressure ratio RS equal to, within the bracket, 1 plus eta S into delta 0 divided by T0, 1 to the power gamma by gamma minus 1, where eta S is the small stage isentropic efficiency and delta 0 is the stage temperature rise. Now, if we consider that the stages are of similar design and let n be the number of stages, then the overall pressure ratio of the compressor RT would not be equal to Rs to the power n. This is because of preheating effect. Thus, what I like to say that even if the stages are of similar design, the pressure ratio in each stage would not be equal. However, temperature rise for each stage would be equal. Thus, the overall temperature rise for the compressor T02 minus T01 would be equal to N into del T0. And further I can write that eta Pc into gamma by gamma minus 1 is equal to N divided by N minus 1, where N is the polytropic index for the compression process. Here N would be greater than gamma. Now, if we approximate that the compression occurred through large number of stages, then eta S can be approximately equal to eta Pc, and this will yield eta S into gamma by gamma minus 1 would be approximately equal to N by N minus 1. Now, the temperature ratio of the compressor, that is overall temperature ratio, T02 by T01 would be equal to 1 plus N into del T0 divided by T01. Now I have expressed the temperature ratio, thus I can express the pressure ratio. Thus overall pressure ratio can be related as P02 by P01 is equal to T02 by T01 to the power N by N minus 1, where N is the polytropic index. Now I have already told N can be related with now eta S and gamma, as I have considered eta S is approximately equal to eta Pc. Thus I can write RT, that is overall pressure ratio, would be equal to, within the bracket, 1 plus N into del T0 divided by T01 to the power eta S into gamma divided by gamma minus 1. Equation number 22. Thus equation number 22 will give us the overall pressure ratio for the compressor if N be the number of stages and eta S is the stage efficiency, that is small stage efficiency, and del T0 is the stage temperature rise, which can be related to del Ts is equal to lambda into Cz into U divided by Cp into 10 beta 1 minus 10 beta 2. Thus here I have illustrated the process of evaluation of overall pressure ratio of a multi-stage compressor where the stages are of similar design from the stage temperature ratio. Thank you for listening.